First of all, I would like to thank the organizers for giving me this opportunity to present my research over here. So the title of my talk is Thermodynamic Trade-off Relation in Stochastic Resetting. Let's first start with some preliminary introduction to such problems which are very much prevalent in nature and day-to-day life, such as foraging, which means that animals search for food or shelter. It can be data search, it can be visual search, where one tries to locate someone in a crowd. And I'm sorry, and there was some writing over here, but let's carry on with it. So the stochastic resetting has proven to be an excellent such technique in this regard, where the first model was put forward by Majumdar and Evans in this. So these references are not here, unfortunately. I forgot, I gave a new version, but it's not working. So here in this initial model, there is a Brownian particle diffusing in a colloidal medium, where the particle is reset at random times in a predetermined position, which is called the resetting position. And in this way, when the particle moves, and it is very easy to reach the target in a finite time. And this helps the mean fast passage time to reach the target at a finite time. So, but before going into the next slide, I would like to point out that this instantaneous resetting in these cases is not possible in actual life. So, which is shown by this experiment over here, where they have considered a Brownian particle in a 2D colloidal system, and the resetting in this experiment has been done in finite time. This kind of systems has also been studied theoretically in this by this group, and there are many theoretical works, but this is just one example of this. So, what is the exact statement of the problem that we have considered? So, we considered a Brownian particle that is diffusing freely for some time. At one point of time, when the reset phase starts, we switch on a trapping potential, which is centered at the resetting position, and allow the particle to ultimately come to this resetting position. The moment the particle reaches the resetting position for the first time, we stop the resetting phase or the return phase and switch off the potential, and then again the diffusion phase follows. In this way, the particle reaches to the target in finite time. And this is given by these dynamical equations over here. So, since we are using trapping potential to facilitate the return of the particle to the resetting position, there is an energy input in the system. So, the question that we ask over here is that what is the minimum searching time or the minimum fast passage time for a given limited energy which is supplied to the system? For that, we need to calculate two quantities. One is the mean fast passage time, and the second is the work done on the system or the energy input, and try to find a relation between these two quantities. First, so the mean fast passage time in this kind of a system is calculated, and the expression for the mean fast passage time is given by this. So we could only calculate it analytically for linear potential, but for higher order potentials, it's very tough to do anything analytically. So here, the mean fast passage time for this with stochastic return is given by the instantaneous mean fast passage time plus an extra factor. This extra factor is inversely proportional to the potential strength A. And as you can see that as the potential strength goes to infinity, this extra time goes to 0, and this whole problem converges to the instantaneous resetting case. So if you plot this one over here, you see this same non-monotonic behavior, the non-monotonic behavior being given by this first factor. The second factor is basically shifting it higher above the instantaneous case. The next thing is the thermodynamic cost. So the thermodynamic cost is the work that is done on the system at the moment when the trap is switched on. During this whole process, the trap remains unchanged. So one actually, so effectively the calculation of work boils down to the calculation of the number of descent that is happening in a single trajectory. So if we calculate the average work for, again, for the linear potential, we could do it analytically. And this expression from here, you can see that the average work is proportional to the potential strength. So if we want to obtain instantaneous results of the instantaneous resetting cases, we need to provide a large amount of potential strength, which in turn requires infinite amount of work to be done on the system. So for these kind of cases, we want to calculate this optimal first passage time. So we have this average first passage time, which is given by this expression, and this average work over here. If we just replace this one in this equation, and one can get a relation between the average first passage time for this kind of a system with respect to the average work done on the system. And as you can see that
2 plus 2 minutes.
And as you can see that there is the average mean first passage time depends inversely on the average work that is provided to the system. So the more the work we do, the lesser will be the mean first passage time in this case. So if we try to plot this minimum value of this mean first passage time, you can see that the minimum value can be decreased only with increase of this work done on the system. So for a particular finite or limited amount of energy that one can have, the mean first passage time can be optimized only that much. For the next thing is that we couldn't do any, we considered different trapping potentials of this kind of a form. We couldn't do any kind of analytics for this case. But what we tried to do is that we considered this Txs, which is the excess amount of time on an average that is required for a system with finite time return over the optimum instantaneous average first passage time. Sorry. And we plotted this one as a function of the work done on the system. So here what we wanted to show is that there are two parameters. One is the potential strength and the resetting rate. For these two quantities, we have calculated the average work, and we have calculated this excess time. What we have showed here through simulation is that when we consider a linear potential like this of this form, this bound actually provides a lower bound for every type of combination of potential strength and resetting rate is considered. So with this, we have these take-home messages, which are that the resetting process with finite time return phase drastically changes the first passage time to reach the target and depends on the confining potential. And given finite thermodynamic resource, there exists a trade-off between the first passage time to reach the target and the work done during the process. So this work has been done with these people, Jain and Hingu Park. Thank you.